Hello everyone, I am Surendra, Master Teacher of Mathematics in Vedantu. I have brought a series for ISI preparation and also for CMI. In my last session, I discussed many questions on recurrence relation. Today also I will be talking about same recurrence relation, but today I will tell you how you can solve for nth term of that recurrence relation. What is the meaning of solving or solution for that? Please understand. Here you can see there are two relations. One is an is equal to an minus 1 plus an minus 2. That is one very famous series known as Fibonacci sequence. Whereas another one is an is equal to an minus 1 plus 3. It looks very easy because here you can see it has a property that difference of nth term with the n minus 1th term is 3. So it is just AP. And suppose a1 is also given, then this an can be written directly a plus n minus 1 into d. So this will be 3n if I use a as 3 also. So you can see that an is 3n here. So if I need to find a100, I think I can write directly. I don't need to write a1, then a2, then a3, then a4. I can write a100 directly. But is it possible in this case also? That is the question. That is the meaning of when I'm saying the solution of an. Can I write an directly as a function of n? Let us try to understand that. So answer is definitely yes. Okay, but how we do this thing, please understand. First, let me tell you different type of recurrence relations. So you can see I have written here 1, 2, 3 and 4 because these two are same only. So 4 different type of recurrence relation which I am calling them as first order recurrence relation. Why I am calling them first order? Because an, that is nth term, is dependent upon its previous term only. In all these 4 relations you can check. Although in first one, this an minus 1 is also multiplied with fn and added with gn. In second one, you can think of gn is 0. In third one, you can think of that fn and gn are constant numbers c1 and c2. Whereas in fourth one, some expression of an minus 1 is written in the reciprocal also. So if you will cross multiply, you will find an getting multiplied with an minus 1, and on the right hand side, linear terms of an and an minus 1. So I have taken few important category of recurrence relations, and I will then discuss how to solve them one by one. In fact, I can also call this as linear recurrence relation. This is also linear because there is no power of an or an minus 1, and there is no multiplication of an with an minus 1 as well. Only fourth one is non-linear, all others are linear. Okay, so let us try to solve first one here. First order recurrence relation of this type. So I have taken one example here. Find nth term of the sequence. A1 you are given as 1. An plus 1 is n into an plus n minus 1, where n is 1, 2, 3 and so on. I will tell you the general approach first, and then I will solve this question also. So what is the general approach? Please try to understand. If we know what is fn, then definitely we know what will be fn minus 1. We will know what will be fn minus 2 and so on, f2 and f1 also. Okay, now if I write this product as, let us say, p, okay, and I divide this given equation by p, I am dividing this equation 1 by p. So tell me, do we get an upon, I think this will be product till n terms. Can I write this as pn here? Okay, whereas on the right hand side you can check it will be p of n minus 1 because this product will not contain fn, so product only till n minus 1 terms, plus gn upon pn. Now we will call this as, let us say, bn, then this will become b of n minus 1. So it can be seen that bn minus 1 is equal to gn upon pn. Now writing n is equal to 1, n is equal to 2, or maybe starting with 2, then 3, then 4 and so on up to n, and adding them, I think this becomes bn method. It can be checked easily. You will get bn minus b1. On the right hand side it will be g2 upon p2 plus g3 upon P3 and so on. It will go up to Gn upon Pn. Now I assume here that this summation on the right hand side will be solvable, and then formula for Bn can be obtained, and then formula for An can also be obtained. Okay, now same thing I am going to apply in this question which I have written here. So let us go to the next slide. Here you can see Fn is n. Okay, so Fn minus 1 will be equal to n minus 1. Okay, now this Pn, you know, it will be just product of these things. So what I will do, I will divide both sides by n factorial. N minus 1 and so on, their product will become n factorial, and we will get here an plus 1 upon n factorial minus, I can write it right on the left hand side, it will be n minus 1 factorial, and on the right hand side it will be n minus 1 upon n factorial. N minus 1 upon n factorial can also be written as 1 upon n minus 1 factorial minus 1 upon n factorial. Now if I write n is equal to 1, okay, this will become a2 upon 2 factorial, a2 upon 1 factorial, not 2 factorial, 1 factorial minus a1 upon 0 factorial is equal to 1 upon 0 factorial minus 1 upon 1 factorial. If I write n is equal to 2, this will become a3 upon 2 factorial minus a2 upon 1 factorial, and this will be equal to 1 upon 1 factorial minus 1 upon 2 factorial and so on. Taking n is equal to, I think, n here in the last, so it will be an or maybe in place of n we will be writing n plus 1, and let me use this symbol, not equal to. So this will be an plus 1 upon n factorial minus an upon n minus 1 factorial is equal to 1 upon n minus 1 factorial minus 1 upon n factorial. So if you add all of them, it can be easily seen. This term will be cancelled with this term will be cancelled with the next one, and so on. So we will be having an plus 1 upon n factorial minus a1 upon 0 factorial. On the right hand side again, 1 minus 1 upon 1 factorial will be cancelled, 1 upon 2 factorial will be cancelled, and so on. And on the right hand side we will be left with 1 upon 0 factorial minus 1 upon n factorial. Okay, a1 is also given to us as 1, so it is now very easy to solve that an plus 1 upon n factorial is 1 here, so 2 minus 1 upon n factorial. So I can write an plus 1 as 2 into n factorial minus 1. Yeah, so that should be the answer. In fact, if you want an, because it was for an plus 1, so an will be 2 into n minus 1 factorial minus 1. That will be the answer for this particular question. It can be checked that this is working for n is equal to 1 also. a1 is equal to 1, you can check. If I take n is equal to 2, so a2 would be 2 minus 1, so 1 once again. So let us check whether this relation is also giving us a2 as 1 or not. If I take n is equal to 1 in this relation, just to verify, so a2 on the left hand side, right hand side it will be 1 into 1, so 1 plus 1, n is 1 minus 1, so it is also 1. Same way you can check that for n is equal to 3 also, it should be a3 is equal to 2 factorial, 2 into 2, 4, 4 minus 1, 3. So it can be checked from here that it will be 3 if I put n is equal to 2. Yeah, it is coming out to be 3. So this is how we can solve such questions. I hope that is clear. So I was talking about of this type of recurrence relation. So what to be done? We have to divide by fn minus 1 and so on till f1, and then you will use Vn method or telescopic sum to get the desired result. Now coming to the second one. I think second one is just the special case of first one, in which Gn is equal to 0. So I have not taken an example on this, because in this case I think it will be even easier, because you don't have to take care of the right hand side. Gn is 0. So I have now taken the third case, in which an is equal to c1 into an minus 1 plus c2. Okay, now this can be thought of fn to be c1 and gn to be c2. So you can solve it exactly same way as we did in our previous question. But I will tell you another approach for doing such question. I will tell you what will be the general approach for doing this question. Alternate approach, I will say. Alternate general approach, you can say. What I will try to do, I will try to write an minus k is equal to c1 into an minus 1 minus k. Okay, where this k will be such that if I take k on the right hand side, so k minus c1 into k will be equal to c2. Okay, so this given relation will be exactly same. There will be no change. What I have done, instead of an, I have written an minus k. On the right hand side, taking c1 common, I have written an minus 1 minus k. Okay, and c2 I have not written. Instead, whatever extra term will be coming because of this manipulation which I have done, that is on the right hand side, k minus c1 into k, I have taken that as c2. So my k value will be equal to c2 upon 1 minus c1. So if I take this thing, I think you all understand. Now I can take this as bn, and this will be equal to c1 into bn minus 1. So this will become a GP, isn't it? With common ratio as C1. So here Bn can directly be written as C1 power n minus 1 into B1, or if we know B0, then we can write this as C1 power n into B0. And here Bn will be an minus k, and B0 will be a0 minus k. So the value for an will be C1 power n into a0 minus k plus k. So that will be the final answer for this kind of recurrence relation. I think that is quite logical and easy to do. Okay, although we can definitely do this type of questions by first method also. Now I will show you how such questions can be done by both the methods. I will now do both the methods here. So method 1 here, please see. I can write this as an minus k as I told you, and on the right hand side half common an minus 1 minus k. Okay, now k is unknown, but k should be chosen such that values doesn't change on the right hand side. So right hand side it was minus 3. If I take this k that side, I think I will get k minus k by 2, and it should be equal to minus 3. So this will give you k is equal to minus 6. Okay, so what we are getting? We are getting an minus 6, an plus 6 rather, and this is equal to 1 upon 2 and an minus 1 plus 6. So this is a GP. If I take this as Bn, this will become Bn minus 1. So this will become a GP with common ratio 1 by 2, and we can write directly it as 1 upon 2 power n into B0, because we are given A0 here, so I am taking this till B0, not B1. If it would have been B1, then power on 1 upon 2 would have been n minus 1. Okay, and now this Bn, if I write this as an plus 6, this will be equal to 1 upon 2 power n, and B0 will be A0 plus 6. Let me use this space. So an will be equal to 1 upon 2 power n, A0 plus 6. If I write, it will be 6 plus 6, 12, plus 2 root 3, A0 plus 6, and minus 6 I have to do. So that will be the answer for this recurrence relation. Okay, now if I have to do it by my first method, if you remember, I told you that we will be dividing both sides by fn n times, fn minus 1 and so on. And here you can check fn is actually 1 by 2. Let me show you that relation here. Fn is actually multiplied with an minus 1. So an minus 1 is multiplied by half, so fn is half. So what I will do, I will divide both sides by fn minus 1 and so on. But because fn is a constant, so it comes out to be 1 by 2 power n. And this will be equal to an minus 1 upon 1 by 2 power n minus 1 here, and minus 3 upon 1 upon 2 power n. So here you can see it becomes 2 power n into a power n, and let me bring this also this side. So 2 power n minus 1 into a n minus 1 will be equal to minus 3 into 2 power n. We can call this as bn, this as bn minus 1. So this bn minus 1 will be equal to minus 3 into 2 power n. Now putting n is equal to 1, I think I can put 1 also, 2 and so on, and last n, and then adding them we will get bn minus b naught, and this will be 3 common, and it will be gp with first term 2, then 2 square and so on, 2 power n. So here we will get minus 3 into 2 power n minus 1 upon 2 minus 1. So my bn comes out to be minus 3 into 2 power n minus 1 plus b naught, and b naught, okay, b naught. And what is bn? Bn here is 2 power n into an. 2 power n into an is equal to minus 3 into 2 power n minus 1. And what will be b naught? B naught means will be a naught only, because 2 power n minus 1 will be 2 power 0, that is 1. So b naught is a naught. So here it will be 2 into 3 plus root 3. So if you divide by 2 power n, I think we will get exactly same thing that we have got here also. Let me check. Yeah, it is coming out to be exactly same thing, because 2 power n will be dividing, what are the constant term? I think 3 into 2 6, and here is 3 only. I think I have made some mistake. Yes, I have made one mistake. First term was not counted here, so this will be 6 here. So that was the mistake. Now everything will be same. Okay, so that is second type of recurrence relation that we can solve easily. Now coming to one more, in which some term of an minus 1 are written in the numerator and some of them are written in the denominator. Also, if you multiply, if you cross multiply, then an minus 1 will be multiplied, and we will be having linear terms of an and an minus 1 also. Now example is given here. I will show you how to do this question through example only, then we may discuss separately how this general approach would be. So if I multiply, cross multiply, we will get 2 into an minus 1 plus an is equal to 3 times an minus 1. Okay, now if we divide both sides by an and an minus 1, so this will be 2 plus 1 upon an minus 1. On the right hand side it will be 3 upon an. Now I hope you all would have guessed it already that I am going to write 1 upon an as bn and 1 upon an minus 1 as bn minus 1. So then this sequence now will become 3 times bn minus, I can write this as bn minus 1 is equal to 2. Okay, now I think this is that third type. I mean to say this one. So what I will do, I will have two methods actually, but I will use the first one, in which I will try to write 3 common bn minus k equal to, I will write bn minus 1 minus k. Okay, now k will be what? If you take this 3k minus 3k that side, I think 2k should be equal to 2. So k should be equal to 1. So here we should get b 3 times bn minus 1 is equal to bn minus 1 minus 1. Let me check once again if this is the same relation as this or not. So 3bn minus bn minus 1 is equal to 2. That is absolutely correct. So you can check in terms of bn minus 1 or bn minus 1 minus 1, it is becoming a GP. So I can write this as directly 1 upon 3 power n into b naught minus 1. If we can go up to b naught, and here b naught will be, because b naught is 1 upon a naught, and a naught is given in the question as 1 by 4, so this will be 4. So here we will get this as 1 upon 3 power n minus 1. So my bn is actually 1 plus 1 upon 3 power n minus 1. And hence this an can be written out directly after calculating bn. So this will be, if I take LCM, so here it will be 3 power n minus 1 plus 1 and 3 power n minus 1 here. So that is the answer of this question. Now coming to second order recurrence relation, that means an will be dependent upon its two previous terms. Okay, and this is actually used in many questions. You will find in JEE Advanced also, and in some questions in ISI and also. So how to solve such questions, please try to understand. I will assume that we can write P as alpha plus beta and Q as minus alpha into beta. In fact, if you remember, such kind of things are done in quadratic. When we split the middle term, then we always try to write that middle term as sum of two numbers whose product is actually the leading coefficient and the last that constant term. So that is something what we are trying to, that is something that I am trying to do here. So if we can write P and Q successfully with alpha plus beta and minus alpha beta, then this relation will become an is equal to alpha plus beta into an minus 1 minus alpha beta an minus 2. Now I can write this as an minus alpha into an minus 1, and on the right hand side it will be beta common, an minus 1 minus it will be alpha into an minus 2. Now I think you can see it clearly that this expression, if I call it as Bn, this will be called as Bn minus 1, isn't it? Which means if we keep on doing the same thing again and again, we can write this as B beta power n minus 1 into a1 minus alpha a naught. I think all these things are constant. So my an will become equal to alpha into an minus 1 plus beta power n minus 1 into a1 minus alpha a naught. So if you check, this is something what we have done here. Let me remind you, fn into an minus 1 plus gn. Okay, here in place of gn we have beta power n minus 1 into this a1 minus alpha a naught, and in place of fn we have alpha. Let me write that relation here. An is equal to fn into an minus 1 plus gn. Okay, now this fn is a constant alpha. So if we use previous methods that we did in our previous two questions, I think we can write a final solution for an in terms of alpha power n, whose coefficient can be a, and exact value of a can be calculated, but I'm avoiding writing at this point of time, but you understand because we have done these things already before, plus b into beta power n. So I hope you understand that if your this recurrence relation is of second order, then an will be actually sum of two GPs. Actually, nth term, sum of nth term of two GPs. And what are these common ratios alpha and beta? If you notice it here, I took alpha plus beta as P and alpha beta as minus Q. So isn't this, please understand, or I should say where alpha beta are, so I should say where alpha beta are roots of x square minus px minus q is equal to 0. Can you notice it? Sum of roots will be p, which is alpha plus beta here. Product of root will be minus q, so that will be alpha beta here. So please try to understand one very strong correlation, or I should say one relation with this recurrence to this quadratic, that assume that an is 1 degree higher than an minus 1, an minus 2 is 1 degree higher than an minus 1 is 1 degree higher than an minus 2. Hence you can think of this as a quadratic, or simply think of that an will be equal to some constant c times x power n, and where x may have multiple values. So if you put c into x power n in this relation, let me call this as equation 1, we will get this to be c into x power n is equal to p into c into x power n minus 1 plus q into c into x power n minus 2. So you will get the same quadratic here, that x square minus p into x plus minus q is equal to 0. So what we have to do in such questions, please try to understand, we have to create one quadratic corresponding to this recurrence relation, and we call this kind of equation as characteristic equation. Characteristic equation. Once we know this characteristic equation, we will find its root alpha beta, and then my an will be of this form. An will be of this form, and a b will be found using initial values a0, a1 or a2. Okay, alpha beta will be found by solving this quadratic only. So please see, this is one example I have taken. Solve the recurrence relation an is equal to an minus 1 plus an minus 2, given that a0 is 1, a1 is 1. So if you remember, this is the famous recurrence relation called as Fibonacci sequence. So what will be my corresponding characteristic equation? You can write it directly also, or if you have confusion, you can write this as c into x power n. So if you put it here, you will be finding c is getting cancelled, and we get x square here, x plus 1 here, or it will be x square minus x minus 1 is equal to 0. So that is my characteristic equation for this recurrence relation. And if you solve, you will get the roots as 1 plus or minus root 5 upon 2. So here alpha will be 1 plus root 5 by 2, and beta will be 1 minus root 5 by 2. Okay, so what will be my next step? So I can think of that an should be a into alpha, which was 1 plus root 5 by 2 whole power n, plus b into 1 minus root 5 by 2 whole power n. Now a and b can be found using the initial values or the values a0, a1. If I put a n is equal to 0, we will get 1 equal to a plus b. If I put n is equal to 1, we will get once again 1 here, and that will be a into 1 plus root 5 by 2 plus b into 1 minus root 5 by 2. Okay, as a plus b is 1, so you can take 1 by 2 common. A plus b you can write as 1, and if you take root 5 by 2 common, you will get a minus b. So from this, suppose this is equation number 1, we will get a minus b to be equal to this 1 minus half is half, so 2 will be cancelled. So it will be 1 upon root 5. Let me check if this is correct or not. Yeah, so this will be 1 by root 5. That is my equation number 2. So solving 1 and 2, we will get a to be equal to 1 by 2, 1 plus 1 upon root 5, and b will be 1 upon 2 into, I think, 1 minus 1 upon root 5. We can write this as root 5 plus 1 by 2 root 5 also. Here will be plus, and this will be equal to root 5 minus 1 upon 2 root 5. So here my nth term an can be written as, you can check now, 1 by root 5 outside, and this will be 1 plus root 5 upon 2 whole power n plus 1 it would be, because n was already there, and minus sign because here it is 1 minus root 5 and here it is root 5 minus 1. So 1 minus root 5 upon 2 whole power n plus 1. So that is the answer for this Fibonacci sequence. Although it looks like that base 1 plus root 5 upon 2 is too big number or too complicated number, you can say. So if somebody is looking for a10 directly, you will have to use binomial expansion or something of that sort to get a10 directly. But let me tell you, if these roots were not irrational, they would have rational numbers like 1 or 2 or 2 or 3, then I think it was quite practical to find A10 directly by this method also. But this is how we solve such recurrence relations. Now let me tell you, if you have recurrence relation of third order in which not only an is connected with an minus 1 and an minus 2, but there is an minus 3 also, then also process is same. Please see what we are going to do. First we will be finding the characteristic equation, and characteristic equation I think I can write it now directly. If I take an as c into x power n, an minus 3 will be 3 degree less, so x power n minus 3. So if I divide by x power n minus 3, I think characteristic equation will be x cube minus 7x square plus 15x minus 9 is equal to 0. Now if we solve this cubic, you can check its factors comes out to be x minus 1 into x minus 3 whole square is equal to 0. Yeah, that is correct. Now let me tell you, if your characteristic equation has roots as 1, 3, 3, that is repeated root, then there can be little confusion that should we take an as a into 1 power n plus b into 3 power n plus c into 3 power n. But I think you understand, b and c can be merged into one. B plus c can be called as another constant. So this cannot be solution of this equation, because this would have been solution of that recurrence relation where this characteristic equation was a quadratic whose roots were 1 and 3 only. So this is not correct. Please understand, this is not correct. Rather, correct thing is that, please understand, for repeated root what we have to do. For single root we will go with the same approach, but for repeated root what we will do, we will write b plus n into c, b plus n into c into 3 power n. Okay, if root would have been repeated 3 times actually, then maybe here there will be 3 terms. I will tell you the general case also, but let us focus on this as of now. So my an will be this thing. Now because we are given 3 values, so if I put n is equal to 0, our equation will be 1 is equal to a plus b only. Okay, and if I put n is equal to 1 here, then a1 is 2, so that will be equal to 2 is equal to a plus b plus 2c into 3. And if I put n is equal to 2, then it is 3 here, and this will become a plus b plus, and if I put n is equal to 2 here, that will be 2c here into 9. I think I have made one mistake here. Here it will be 1 only, b plus c, yes. Now we have to solve them. Okay, if we solve them, we get the answers to be a as 0, it can be checked, b will be equal to 1, and c will be equal to minus 1 upon 3. It can be checked. Let us check. First equation is satisfied, a plus b is 1. Second equation, b plus c into 3, so it will be 2, that is correct. And the third equation, b plus 2c, so 1 minus 2 by 3, so 1 by 3 into 9 is 3, so that is absolutely correct. So the solution for this recurrence relation would be an is equal to 0, then b as 1 minus 1 upon 3 into n, or let me write this as n by 3, and this will be multiplied with 3 power n outside. So that will be the answer of this recurrence relation. Okay, now let me show you the general linear recurrence relation of this type. Suppose you are having r order of this was second order recurrence relation, this was third order recurrence relation, this is r order recurrence relation where an is connected with an minus 1, an minus 2, an minus r also. So this is r order. So what will be the characteristic equation? We will be taking an as x power n, an minus 1 as x power n minus 1. Constant you can ignore because it is going to be cancelled otherwise also. So this will be my characteristic equation. Now, if you solve this characteristic equation and we get its roots to be alpha 1, alpha 2, alpha r, if they are all distinct roots of this characteristic equation, then an will be directly a1 into alpha 1 power n plus a2 into alpha 2 power n and so on, ar into alpha r power n. Okay, and by initial values you will find a1, a2 and so on. But if roots are not distinct, rather roots are alpha 1, alpha 2, alpha k, where each root alpha 1, alpha 2 appear mi times, alpha 1 appear m1 times, alpha 2 appear m2 times and so on, alpha k appear mk times, then this solution for this recurrence relation will be an is equal to, please understand, alpha 1 power n is multiplied with a bracket in which you can see there is not a constant only a11 but a12 with n, then a13 with n square and so on, then a1 m1 with n power m1 minus 1. Okay, so if it is repeating, this root is repeating m1 times, so you can see there will be m1 terms only. Similarly, alpha 2 power n will also be multiplied with a bracket where number of terms would be m2, and similarly for this last root. So this seems to be complicated or very complex method here, but that is how we solve this thing. Mostly we do not require repetition, or at most, as I did in our previous question, repetition will be 2 times or maximum 3 times. It cannot be more than that. Otherwise there will be too many constant involved and there will be no point using this kind of methods to solve such questions. Okay, so this is how this second order, third order, I think you all have understood how we can solve it. Now coming to next, general linear recurrence relation. Linear, all the powers of an minus 1 are 1 1 1 only. No an minus 1 or other an minus r are multiplied, so they are linear. But we are now having on the right hand side fn also, which we were not having in this kind of equations. If you remember, in these questions I took 0 only. If you write this also, it will be an minus 1 minus an minus 2 is equal to 0. But if you are having some function of f on the right hand side, how to solve it? Now please understand, in such question what we will do, we will make two parts of such solution. One will be corresponding to the homogeneous equation. Homogeneous means assume right hand side was 0. This will be corresponding to C naught an plus C1 an minus 1 and so on, plus CR an minus r is equal to 0. So this will be exactly same what we have done before in these two examples, and then I told you the proper method for this kind of recurrence relation. Okay, and then there will be one more part of the solution that we call as particular solution, and this particular solution will be corresponding to fn. Okay, now what is fn? This a and p will depend upon that fn only, but there is no means set process to find this a and p. We will go mostly by observation that what fn is. Like in this example you can see fn is a quadratic. Okay, so here what will happen, let me tell you, that an minus 3 an minus 1 is equal to 0. If I write, its characteristic equation will become x minus 3 equal to 0. Yes or no? Because it's a first order only. In fact, this could have been done by use of GP also, but I'm doing it using characteristic equation now. So an has to be a into 3 power n, because only root is 3, and because we are given a naught as 3. But yes, just wait 1 minute, because let me find the solution for a and p also. Then after writing both the solution together, we will find the value of a. We will not find a at this point of time, because this solution is only for homogeneous part of this equation. So let me write this homogeneous equation. So this solution is corresponding to homogeneous. Now coming to this second part. So please understand, for this Fn is equal to 2 minus 2n square. I think it can be observed that an has to be some quadratic. Then only we can get this kind of relation on the right hand side, isn't it? So an can be taken as an square plus bn plus c, and then we will put the value of an into this, and we will get an square plus bn plus c minus 3 times, and here it will become a into n minus 1 square plus b into n minus 1 plus c is equal to 2 minus 2n square. Okay, now we will be comparing the coefficients and we will get the values of ABC. Like for n square, if I compare this coefficient on the left hand side will be a minus 3a, and on the right hand side it is minus 2. So the value of a comes out to be 1. I will like to leave the calculation for you. You can check that comparing the coefficient of n and constant will give you the values of b and c also. And after doing all the calculation, I think b comes out to be 3 and c comes out to be 2. It is just simple calculation work, so I am not doing it now. So this is what we will be getting as ABC. So what is my particular solution? I think I forgot this P here. So A and P, particular solution is n square plus 3n plus 2. So what will be the complete solution? Complete solution will be A and H, homogeneous part, plus A and P, that is particular solution. So here it becomes A into 3 power n plus n square plus 3n plus 2. And because a naught is 3, so putting n is equal to 0, we will get 3 is equal to a plus 2, which gives a as 1. So the final answer now is this 3 power n plus n square plus 3n plus 2. That's it. So this completes the solution of this question. Okay, now coming to this question, it says let an be a sequence such that an is equal to 3an minus 1 minus 2an minus 2 plus 2 power n greater than or equal to 2. A naught is 3, a1 is 8. We have to find an. So you can see this is again a linear recurrence relation, but there is some fn also on the right hand side. So if I bifurcate it in two parts, one is homogeneous equation. So homogeneous equation would be an minus 3an minus 1 plus 2an minus 2 is equal to 0, and then corresponding to this, the characteristic equation would be x square minus 3x plus 2 is equal to 0, whose roots are either 1 or 2. So for homogeneous part, the solution should be a and h equal to a into 1 power n plus b into 2 power n, which I can write as a plus b into 2 power n. Now coming to this particular solution part, or corresponding to 2 power n. Now because this fn is 2 power n, so my assumption for an for this 2n should not be polynomial function, isn't it? Because polynomial function, if you take an, then these an minus 1, an minus 2 cannot give you 2n. So my assumption here should be in terms of 2 power n. I hope you are getting it. But please understand carefully. Here already 2 power n term is there in that homogeneous part. So for this particular solution, we will not take that solution to be a and p is equal to c into 2 power n. It will not be taken. Rather, we will take this into n. Please understand, we will take this into n. This is exactly similar to what I told you when there is a repeated root. If you remember what we took, b plus nc into 3 power n. You can remember this as that there are 2 power n coming from homogeneous part also, and from that fn also. So instead of taking c into 2 power n, we will be taking n into c into 2 power n. Okay, and now my complete solution can be written as an is equal to a plus b into 2 power n plus n into c into 2 power n, and I will now put this value of an into that given equation, which will be now a plus b into 2 power n plus n into c into 2 power n. On the right hand side, it will be 3 into a plus b into 2 power n minus 1 plus n minus 1 into c into 2 power n minus 1, okay, minus 2 into, and here it will be a plus b into 2 power n minus 2 plus n minus 2 into, I think this will become c into 2 power n minus 2 plus 2 power n. Okay, so this is what we will get. Now if you solve it, in fact you can check this 3a minus 2a will be cancelled. Okay, some more terms will be cancelled, and if you do the calculation comparing the coefficient, what we will be getting, I think we will be getting here b to be equal to, I think c can be found. Yeah, c can be found. C will be coming out to be 2. I think term of b will also be cancelled here. You can check b into 2 power n, and here 3 into b into 2 power n minus 1, and this 2 into b 2 power n minus 2. These two will cancel that term of b also, it can be checked. So only term that remains is c. Okay, and if you solve it, you will get c as 2. Okay, so my an will become equal to a plus b into 2 power n plus 2n into 2 power n. Now we have to use these a0 and a1. Putting n is equal to 0, putting n is equal to 1, we will get two linear equations, which will be 3 is equal to a plus b and 8 is equal to a plus 2b plus 4. So solving this, we'll get a is equal to, I think, 2 and b is equal to 1. It can be checked. Yeah, 2 plus 1 is 3 and 1 plus a is 2. 2 plus 2, 4 plus 4, 8. Yeah. So final answer for this would be an is equal to, let me write the final answer, is 2. Yeah. So it will be 2 here plus 2 power n plus 2n into 2 power n. So that is the final answer for this particular question. Now one more question let us do. This question says an is equal to 2 into an minus 1 plus n plus 2 power n plus 1, where a0 is equal to 0. So here you can see that fn is combination of polynomial and this exponential function also. So first we will be breaking this equation into homogeneous part, which is an minus 2 an minus 1 only, corresponding to which characteristic equation will be x minus 2 equal to 0. So root would be x is equal to 2. So a and h should be equal to a into 2 power n. And then coming to this particular solution. Now coming to particular solution for this fn. For fn, and fn here is n plus 2 power n plus 1. So please understand how we are going to take this a and p. Because of presence of n, we should take this as b into n plus c, that is 1, and we should take 2 power n plus 1, or we can write this as 2 into 2 power n also. And you please notice 2 power n has already been taken in homogeneous part. So here it will not be just d into 2 power n, but it will be d into n into 2 power n. I think I have done this thing now 2 times before. In one question immediately before, where I took n into c, and before that in that cubic also, where I took b plus nc. So wherever repeated roots are there, you have to take this way. So my complete solution of an would be a into 2 power n plus bn plus c plus dn into 2 power n. So that will be my complete solution. Now we will be again writing this an in this equation. So we will get a into, or let me use this only. So this will become equal to 2 times an minus 1, which we can write as a into 2 power n minus 1 plus b into n minus 1 plus c plus d into n minus 1 into 2 power n minus 1 plus n plus 2 power n plus 1. Here it can be checked, this a into 2 power n, a into 2 power n minus 1 and outside 2, they will be cancelled. Okay. Similarly, I think this dn into 2 power n here and dn into 2 power n minus 1 outside multiplied with 2 will also be cancelled. So this term effectively will be cancelled with this. Okay, so what is now left? Let me write that once again. So left things are bn plus c on the left hand side, and on the right hand side it will be 2b into n minus 1 plus 2c, okay, and minus 2d into 2 power n minus 1 plus n plus 2 into, or 2 into, yes, 2 power n here. I think I could have written this also as d into 2 power n. Now if I compare the coefficients of, let us say, n, so we are getting b is equal to 2b plus 1, which will give b as minus 1. If I compare the coefficients of 2 power n on both sides, so left hand side it is 0, on the right hand side it is minus 2 minus d plus 2, which gives d to be equal to 2. And then comes the constant term. Constant term on the left hand side is c, on the right hand side it is minus 2b plus 2c, okay, and this will give I think c to be equal to 2b, that is minus 2. Okay, so let me use that space to write the remaining solution. So my an will be equal to a, I think we have not found, so I will write a into 2 power n. B we have found as minus 1, so it will be minus n. C we have found minus 2, and D we have found 2. So I can write this as n into 2 power n plus 1. Okay, now the initial condition, putting n is equal to 0 will give 0. So this will be a minus 2. So a will be 2 here. So a, if it is 2, then this is also 2 power n plus 1. So final answer is an is equal to minus n minus 2 plus n plus 1 common and 2 power n plus 1. So that is the answer. Let me write it once again. Into 2 power n plus 1. So that is the answer of this recurrence solution. And minus n minus 2 plus n plus 1 into 2 power n plus 1. Okay, now this is the time for teaser question. But before that, there is few things. Let me just repeat, or I just summarize that in general linear recurrence relation, we will be solving this homogeneous part first, according to whether roots are repeated or roots are not repeated. You know both the cases how to solve, and then we will find particular solution for fn and we will add them. If in your particular solution, if you see any repeated root to be coming, then you have to take care that accordingly, as I have discussed in this session. Okay, now before coming to the teaser session, dear all, if you are preparing for JEE Advanced, then this Vedantu Eklavya is one big thing for you. So please go through Google to know what is Vedantu Eklavya. It will be very helpful for your JEE Advanced preparation. I am sharing with you this notice board of topper pod of Vedantu, where all important information regarding batches are put. Any new things coming up is put. This is a QR code to join the same, to go through that go through that notice board. So please follow this to come to know what exactly is going on. I think now this is just round the corner, but still, if you are going to write JEE Advanced this year, you can join this channel through this link or this QR code. Also, this link is given in the description box to become a part of this Telegram channel, where we are putting all important information about JEE Advanced. Similarly, for 2023 aspirants and 2024 aspirants, these are the links of respective channels. Please join that. We will be putting all relevant information for you there. We have also created V Impact channel, YouTube channel, where we are putting JEE Advanced solutions, KVPY solutions, and also we will be coming up with ISI and CMI very soon. So please follow this channel. You will find very relevant solutions, many alternate solutions for each questions and solutions are given question wise. It is not that entire paper is solved in single video, so they are given question wise. So that is about this V impact channel. Now coming to this teaser question, I think this is the same question which I shared in my previous session also. Let me repeat it. The n sectors n greater than or equal to 1 of circle of figure are to be colored by k distinct colors, where k is greater than or equal to 3 in such a way that each sector is colored by one color and any two adjacent sectors must be colored by different colors. Let an denote the number of ways this can be done. Then we have to find what is a1, a2, a3, and for n greater than or equal to 4, we have to find a recurrence relation. So this was the question of last session, but now I have added this part that you have to solve this recurrence relation which you will be obtaining. Okay, so if you solve this question, please send your solution to this email ID eklavyaSupport@vedantu.com with the subject line teaser solution maths. We will check your solution, and if we like it, we will reach out to you on the same email ID through which you have sent the solution. Okay, so that is all for today. Thank you so much. Bye everyone.